Good morning. I'm hoping you can hear this. This is E-Day number 2, and I'm just going to pick up and do some notes so that we can hopefully get to the point that we need to be by maybe third period tomorrow. We'll see. I want to talk about lattice energy a little bit. That's where we left off. We started talking about it. I don't think that we got a good definition for it. I want you to think of lattice energy as the energy required to completely separate. So when I say separate, that means we're actually breaking the bonds. 1 mole of a solid, which is the way that we normally find them, solid ionic compound into its gaseous state. So we're talking about the compound is already together. Now what energy is needed to break that crystal lattice apart? When this happens, the way that it happens is the solid structure expands from within, breaking bonds. So internally, bonds are breaking. We're separating that compound into eventually its gaseous state. When I look at lattice energy, and I'm going to say we've been using sodium chloride a lot, NaCl requires 788 kilojoules of energy per mole to actually undergo this change, this bond breaking internally and moving to the gaseous state. Now I can take that, and if you were going to see it as a chemical equation, it would look like this. NaCl in solid form undergoes a reaction, or undergoes a change, and I end up with Na in gaseous form, and I end up with my chlorine in gaseous form. Following that, you would see delta H lattice is equal to 788 kilojoules per mole. That's what it took to break it apart. 788 kilojoules per mole. So I had to add that energy. That reverse process of coming back together or forming that compound again So this is actually the bond formation, not the bond breaking. That coming back together would be an endothermic process, and it would be written as delta H equals 788, negative 788 kilojoules per mole. So think of that as the formation versus the breaking apart. I've got an endothermic reaction going on here versus exothermic up here when I'm breaking it apart. So when I look at these things, I can say that the magnitude of the lattice energy depends on some things. First thing it depends on is the size of the ions. It depends on the charge of the ions. And it depends on, we'll just say, crystal arrangement. So 3 things we have to look at when we're figuring all that out. We also have to look at those 3 things plus the electrostatic potential of can't see that very well. Electrostatic potential of the two charged ions. And when we do this, we actually have a formula that we can plug some things into. E, which is energy, EL stands for electrostatic, is equal to, and I'm just going to give you this to begin with, K, Q1, Q2 over D. And let's look at what those things are. I just said E sub EL is your electrostatic potential. K is a constant. It's actually called the proportionality constant. And it's used a lot in thermodynamics, and we'll learn more about it and where it comes from later. But for now, you just need to know that it's equal to 8.99 times 10, to the 9th joules meters per second. Per coulomb squared. So I think I should rewrite that. 8.99 times 10 to the 9th joule meters over coulombs squared. Now, this D equals distance, and that would be the distance between bonded atoms. My Q1 equals the charge on the first particle, on my first ion, that's going to be in coulombs, and this Q2 equals the charge on the second particle in coulombs. So that gives you an idea of what's going on with each of those variables. It also basically tells us my K is not going to change. My electrostatic potential becomes, really makes me look at 2 things. My charge on my ions and the distance between the ions. So there's really 2 things that that equation allows me to focus on. Obviously, the bigger the D, it affects the electrostatic potential, and the larger the Q1 and the Q2 will affect the electrostatic potential. And we'll come back to this. But as I really just kind of want to focus on this just a little bit, talk about when you look at it, what you should realize. Kind of what I just said here. Can't see that. I would say that by looking at that equation, first of all, for a given arrangement of ions, I could say, number 1, lattice energy increases charge on the particle increases. So lattice energy will go up as that charge on the particle increases. Look at that. This electrostatic potential tells me about lattice energy. My Q1 and Q2 are my charge on the particles. As these things go up, lattice energy is going to go up. The other thing that I should be able to see from there, I want to talk a little bit more about this in a minute, that my lattice energy would decrease as atomic radius increases. This one, the second, is not nearly as important as this is. This tells us more. It depends more on the charge, because ionic radius or atomic radius, either one, I should really clarify that. We know it increases as we move down, it decreases as we move across, but there's really not that much of a change because we're talking about such a small quantity. What influences this lattice energy much more, and the size of the lattice energy, is actually the charge on the particle. So let's look at this for just a minute. Let's say I have CaO, calcium oxide, CSI, cesium iodide, and sodium fluoride. And I'm going to say arrange in order of increasing lattice energy. When you do this, you have to think about the charges on each. So when I look at this, Ca is a 2 plus, O is a 2 minus, Cs is a plus, I is a plus, NaF is a plus, and F is a plus. So I know what matters most is the charge on the ions. The larger the charge, the greater the lattice energy. So I know, if I put my less than arrows in, I know right away I should be able to pick out that my calcium oxide is going to be having the greatest lattice energy because it has the greatest charge. So I'm going to put those guys down here on the end. Then I have to actually go to a periodic table and I have to look at these things. When I look at cesium iodide, I'm down there. When I look at sodium fluoride, I'm up at the top. Well, what happens to ionic radius or atomic radius as I move down the periodic table? What happens? It gets larger, correct? So when I'm down here, I'm actually dividing by a larger number, which helps me to figure that out. So I know that my CSI is actually going to be smaller than my sodium fluoride because sodium fluoride is above it on the periodic table. So it has a smaller atomic or ionic radius, so I would be dividing by a smaller number. So this is like 1 divided by a small number versus 1 divided by a large number, which would tell me then that this, because it's divided by a larger number, would be the smallest of the 3. So basically I can sum that up and say lattice energy decreases as distance between ions increases. So it follows a trend, just like we've been looking at everything else on the periodic table following trends. If I look at my ions of the S and P block, and I do some electron configuration, I can say that electron configuration explains ions formed. And we've talked about that a lot, so that's not like anything new. That happens really nicely in the S and P block. We looked at that, we use them a lot. When I go down to the, or go across the transition metals though, what happens is, my ions here don't, which is different than everywhere else, don't normally have a full outer shell. So they're a little bit odd in that way. Most of them end up to have 3 electrons in their outer shell. Oops, outer shell. So most of them have 3 electrons beyond, I should say, a full outer shell, which is why we see a lot of them form, like I'm using aluminum for an example here, a lot of them will form ions with a 3+ charge. So they're happy to give up 3. After that, not so happy. We've got all kinds of things going on in the transition metals. Remember that we also have ions that are followed by Roman numerals, like tin 2, tin 3. You know, I've got copper 1, copper 2. So we have a lot of things, that's what that said. We have a lot of things in the transition metals that will form multiple types of ions. If I look at silver, remember I showed you that triangle on the periodic table, for example. If I look at silver, silver actually has a noble gas configuration of Kr 4d10 5s1. So it's a little different. So of course that's why it's happy to give this up and form Ag+. That is totally why we see multiple forms of ions here. And when I'm here, the octet rule is useful, but I would say it definitely has some limitations. You have to know what's going on your periodic table to be able to predict what's going to happen with your ions that form in that particular part of the periodic table. So that's why we spend a little extra time thinking about the transition metals. That's why you see that stock system of naming coming into place there, where we say copper 1, copper 2. Later on we'll talk about how one is called cupric and one is called cuprous, depending upon its charge, but we won't get into that right now. So that kind of finishes things up for ionic bonding. Now I just want to hit a little tick of covalent bonding, and then we'll be done for today. So we know already the second top bond type is covalent bonding. I call this bond type 2. So we're going to talk about covalent bonding, bond type 2. Some of the things we should look at are big, broad overview here, beginning with the fact that most chemical substances, let's say most chemical substances do not have ionic character. So most of them do not actually exhibit ionic character, which tells us, there must be more covalent compounds than there are ionic. Most compounds that we actually deal with can be gases, liquids, solids. Remember, when we're dealing with the ionic compounds, we're dealing with solid crystal lattice formation. So again, this is a little bit different. Most of the things that we deal with actually have low melting points. Again, covalent, low melting points. In these covalent bonding situations, we actually see, and you guys know this, sharing of electrons. For example, when I look at my diatomic molecules, and these covalent compounds, we call them molecules, I could actually take, I'll take something really simple here, let's take H2 gas. Actually, if I were to show that as a Lewis structure, a Lewis equation, I would have H plus H yields H2. Of course, this would be gas, gas, gas. And you can see that each of them, when I did this, normally we would put these at the top, but I will tell you when you're showing this bonding, that it's okay to show these electrons in a situation that is similar to how they're going to be shared over here. What's going on when this comes together is that I actually have the nuclei of these hydrogen atoms. They're repelling each other. I have the electron from this hydrogen atom repelling the electron from this hydrogen atom, but I also have the nuclei of both the hydrogen atoms being attracted to that electron. So ultimately, the attraction between the nucleus and the electrons win out, and it actually forms a bond where those electrons are shared. So we probably should make a little note about that. This molecule is actually stable. And that is due to, let's say, due to attractive forces overcoming repulsive forces. Just be sure that you understand what the attractive versus repulsive forces are. Again, electrons want to repel each other. Nuclei want to repel each other. But ultimately, the nucleus of both of these hydrogen atoms is attracted to those electrons, and that attractive force is greater than the repulsive forces between the other things that we've discussed. Let's look at another example of a Lewis structure. I'll just pick another diatomic molecule, and I'm going to say we'll use chlorine here. So let's do a Lewis structure. This would actually be called, or what you would be asked for is a Lewis structure of, we'll say Cl2, the diatomic molecule Cl2. So you should pick up on the fact that this is Cl2, that it's a diatomic molecule. The fact that it's a diatomic molecule makes it a covalent compound, so it has shared electrons. So what I do is I show my Cl, and again, I'm going to position my lone electron. We know Cl has 7 because it's in group 17. I'm going to position my lone electron in the place where it's most likely to bond. So I'm going to go 1, 2, 3, 4, 5, 6, 7. I have 2 of them, so I'm going to do the same thing. I'm going to make my other Cl, and I'm going to go 1, 2, 3, 4, 5, 6, 7. I would draw my arrow, and I would show my bond formation like this. Cl, 1, 2, 3, 4, 5, 6. Here's number 7. And over here, I'll put my Cl. Ooh, that's way too big. 1, 2, 3, 4, 5, 6, 7. Then, what is normally shown is a circle around each of the chlorine atoms, showing that these are my shared electrons. Those shared electrons are called a bonding pair. And I would say that it allows each to get an octet. So it allows each of them to get an octet. Sorry. So these are my shared electrons. These guys up here are called lone pair electrons, or they might be called a non-bonding pair. So bonding pair, non-bonding pair, or lone pair electrons. You'll hear all three of those terms. Now, when I have a situation where my outer shells are full, everybody's happy, everybody has their octet defined as whatever an octet would be, maybe 8, or if I'm dealing with hydrogen and helium, my octet, lots of times it's still called an octet, even though they're happy with only 2. We can call those 2 electrons, because they have a full outer shell, an octet. It's not the most correct thing to do, but there are lots of books that call that an octet. So when a full outer shell exists, like this chlorine up here, I could technically just write this as Cl, Cl with a single bond. I don't have to share necessarily all of those outer shell electrons. When you see this, you should understand both of them have an octet, they're happy, they have a full outer shell. You can actually look at your periodic table and it should be pretty clear to figure out these bonding pairs. If I look at group 7A, we know we have 7 outer shell electrons. That's going to leave me with 1 bonding pair. If I look at 6A, I've got 6 outer shell electrons, so I'm most likely going to have 2 bonding pair. If I look at 5A, I've got, obviously, 3 outer shell. Maybe I've got 7 electrons here, 6 electrons here. Here I'll have 5 electrons. So I would need 3 additional electrons, which means I would have 3 bonding pair. And then I could even look at group 4A, which we know has 4 outer shell electrons. So technically there I would have to have 4 bonding pair. So let's look at hydrogen fluoride. And let's say they're going to form a bonding pair. So I know that I have H with 1 electron plus fluorine with 7. I know that I'm going to get H bonded to F. Fluorine's going to have its octet. Technically, we say that a hydrogen has its octet, and I will just write that when I come down here to make its final structure as HF. This would be called one bonding pair or a single bond. Now let's look at something like water. I'm just trying to give you some examples here. Water, I've got hydrogen plus oxygen, which is going to have, I'm going to set this up so that we can have 1, 2, 3, 4, 5, 6, because I know I've got 2 hydrogens to bond to it. So in the end, I end up with H, 1, 2, 3, 4. I pull one of my hydrogens over here, and I can pull the other one over here. So now hydrogen's got 2, hydrogen's got 2, oxygen's got 8. I end up writing that then as O, bonded to H, bonded to H, and I actually do show my electrons here so that I know that oxygen has a full outer shell. This would have 2 single bonds. If I look at something like, I'm trying to give you an example from each one of these. If I look at something like ammonia, which would be H, let's see, H plus H plus H plus nitrogen, which would have 5. So I'm going to 1, 2, 3, 4, and I'll put my 5th one over here. So I've got all my bonding sites. And then I would end up with N, oh, that's an H. With N, with my 2 electrons over here, single bond H, single bond H, single bond H. So this one, this was group 6, an example from group 6A. This was an example from group 5A. Let's do one example from group 4A. Let's do CH4. So one, I'd probably be better served to put these up here. 1, 2, 3, 4 plus carbon, which has 4 in its outer shell. And I'm going to end up with, write it down here, C, single bond H, single bond H, single bond H, single bond H. So there's my example from group 4A. So that gives you one from 7, 6, 5, and 4 to look at. And I think that's enough for today. I have just a little tiny bit that I'll go over with you tomorrow, and then we should be able to move into lab. I hope you can hear this today. I worked with it a little bit. I did a couple tests, and I was able to hear it. And enjoy your day.